After watching, you'll sleep soundly for 8 hours straight. It's just that good. If you truly want to understand why the universe is so perfect, then we have to start with a mind-boggling number. Richard Feynman, that old guy. Back in the day, he really caused a lot of trouble for this number. At that time, he had already studied how electrons and photons interact. He understood this thoroughly. With this deep insight, he even won the Nobel Prize. But even so, there is a certain specific number that clings to him like a stubborn dog's skin plaster. This number is actually the fine structure constant, the core of quantum electrodynamics. Simply put, it's a number that tells us the strength of electromagnetism. Its value is roughly close to 1/137. But Feynman's theory has a shortcoming. You simply can't calculate this number. You have to measure its value through experiments. Only then can those equations truly be useful. Otherwise, they're just decorations. Even today, scientists are still digging deep, trying to find out where this number actually comes from. Actually, you know, the fine structure constant isn't the only one just sitting there. In our physics theory, in this physical theory, these constants determine how the fundamental components of the universe operate, like how electrons repel each other, or how gravity pulls matter together. It's all decided by these constants. Among these natural constants, some are familiar to us, like the speed of light, Planck's constant. They come to mind easily. But what about some, like quark mixing and the Yukawa coupling, are hidden deep within complex physics mathematical theories? Most people look at them and get confused. If we don't carefully measure and calibrate these numbers, all physical theories are at a loss. They're useless. Obviously, natural constants are the lifeblood of physics. But they also seem to play a crucial role in a much bigger problem. So how should we understand this? We have to dig deep within ourselves. It's like when we dissect the human body. The body is a complex mixture of organs and bodily fluids blended together. Look closer. These organs and fluids are made up of all kinds of individual cells. Each cell has to cooperate with the others, working together to perform the functions of the liver, muscles, or brain. If you look even deeper, each cell is like an intricate, complex ocean. Inside, there are ribosomes, chromosomes, cytoplasm, mitochondria. These smaller components, when the cell is functioning normally, each play their own role. No one can be missing. What about these cellular fragments? They are composed of molecules, proteins, lipids, DNA, and RNA. By this point, the deeper we go, the more complex each layer becomes. But don't worry. Let's keep exploring further. Simplicity gradually begins to emerge. Molecules are made up of atoms. Each type of atom arranges itself in a very complex way. Because of this, complex interactions can occur between them. But chemistry tells us, from hydrogen to uranium, there are a total of 92 natural elements in the universe. In other words, there are only 92 different types of atoms. Let's dive into the subatomic world. Hey, the picture just got simpler. Every atom is made up of 3 types of particles mixed together. There are also electrons orbiting the nucleus. And protons and neutrons are made up of even smaller particles, called up quarks and down quarks. At this most fundamental level, we find matter. Humans, trees, planets, stars, ultimately, are nothing more than these quarks and electrons. Different combinations and permutations. That's all, of course. These tiny particle fragments, there's something that sticks them together. For fundamental particles, this glue is the fundamental force. The atomic nucleus is held together by the strong force. Atoms use electromagnetic force to hold electrons. Gravity pulls matter together, forming planets and stars. Additionally, the weak force also plays a role. It can influence the stability of atoms. In simple terms, we are made up of fundamental particles, assembling from the bottom up. Our physical existence in this universe, put simply, is the external manifestation of the interactions of fundamental forces in the universe. And all these interactions are determined by the values of natural constants. But where exactly do the values of these natural constants come from? Does the universe have to be like this now? From the Big Bang to the present, this is the basic evolutionary process of the universe. Does it necessarily produce the complexity crucial to life? These questions may sound a bit strange at first. Right now, we only know of this one universe. Through experiments, we know the values of these natural constants. They seem to be written into the very structure of the universe. But science is based on assumptions. We often ponder, what if things were different? How would it all turn out? It's not just possible to answer, how did we exist in this universe? How did we exist in this universe? It's even possible to answer. It's even possible to answer. Standing on Earth, we are prone to illusions, often feeling the universe is made just for us, feeling like we stand at the center of the universe, with the sun and stars revolving around us. Actually, since the dawn of human civilization, our understanding of our place in the universe, they were incorporated into developing religious beliefs. Back in ancient Babylon, people believed that our flat, round Earth was surrounded by an endless chaotic ocean. The Greeks and Romans spent their days telling stories about the celestial gods, but once science developed, these fantasies were shattered. In 1543, the astronomer and mathematician Nicholas Copernicus stepped forward and proposed the heliocentric theory, placing the sun at the center of the universe. The Earth became just a small player orbiting the sun. By the 20th century, our place in the universe was diminished again. With the advent of large telescopes, we could see much more clearly. The sun is just one star among tens of billions in the Milky Way, insignificant. Now we know even more. The Milky Way itself is just one among trillions of galaxies in the observable universe, truly tiny. The Hubble telescope has drawn the shape of the universe. We've also measured the distances between galaxies. Einstein, Friedman, and Lemaitre discovered that the universe is constantly changing, continuously evolving and expanding. The universe was born in a Big Bang 14 billion years ago. We now call this the Big Bang Theory. But what insights does this give us? There might be a possible answer from the unique insight of Douglas Adams. In his comedic novel The Hitchhiker's Guide to the Galaxy, he wrote, "Far, far away in a remote place no one cares about, at the very edge of the western spiral arm of the galaxy, there's a small, unnoticed yellow sun. About 92 million miles from the sun, there's a tiny, tiny blue-green planet. On this planet, the life forms descended from humans are primitively astonishing. They see a digital watch and treat it like a treasure, thinking it's incredibly clever. But this is no simple joke. Our insignificant place in the universe has become a core scientific principle, called the Copernican principle. Our current scientific theories are all based on the idea that we don't have anything special developed from that. Looking at the universe from Earth or from elsewhere in the universe essentially makes no difference. We are just observers of the universe." In the 1960s, Princeton astronomer Robert Dicke, wholeheartedly exploring the origin of the universe. This guy is a real scholar in atomic physics and Einstein's general relativity. He made groundbreaking discoveries. These discoveries all stem from his deep thoughts on the birth of the universe. Dicke pondered our place in the universe. But he doesn't take the usual path. He doesn't think from the perspective of space. He realizes that creatures like us couldn't have just appeared at any random point in cosmic life. Billions of years ago, the universe lacked carbon, oxygen, and other heavy elements. These elements are still hidden inside the first-generation stars. They have to wait until these stars reach the end of their life. Only then does the universe develop complexity and the raw materials for life. Another 100 billion years later, stars like the Sun will also cool down and turn into white dwarfs. By that time, the main stars in the universe will be faint red dwarfs. These tiny stars have a low probability of nurturing life. So, he came up with an idea. Between the early universe and the late universe, there is a window of time, during which life can thrive and grow within this window. This is the golden age of cosmic habitability. Of course, we realize that we happen to be living in this particular phase of cosmic history. There's nothing surprising about that. We're not just wandering aimlessly through the long life cycle of the universe, glancing around at random. Instead, it's during cosmic evolution that this particular period became suitable for our survival. That's how we established our footing. Although at first glance, this discovery doesn't seem to be earth-shattering or revolutionary, it did indeed shake the foundation of Copernican principles. In 1973, a conference was held in Krakow, Poland, celebrating the 500th anniversary of Copernicus's birth. As a result, the conference, things have become more complicated. Australian physicist Brandon Carter took the stage to speak. He directly applied Copernicus' theory to the perspective of humans observing the universe. He said that although our position in the universe may not be at the exact center, to some extent, the fact that we can exist here is a privilege. Why? Because it takes hundreds of billions of years of successive stellar generations to turn light into the heavier elements necessary for our survival. Carter also further pointed out that a star's lifespan depends on the physical processes in its core. Gravity forces the stellar core to contract intensely, increasing its density and pressure to extreme levels. Under such conditions, new elements are formed through nuclear reactions at a certain rate, and this nuclear reaction rate is determined by electromagnetic, strong, and weak nuclear forces. These fundamental forces work together to govern it. The elements produced inside stars, the iron in the Earth's core, and the oxygen in the oceans, as well as the fundamental carbon for all life on Earth. That's how it all came to be. So, for the first time, Carter proposed a new concept that contradicts the Copernican principle, called the human-centered principle. Our existence. It was about 14 billion years after the universe was born. It is precisely because the fundamental forces governing life have reached a super-delicate balance, combined with the star evolution cycles and a bunch of other factors, all acting together. Considering all this, we can't help but ask, what if we are this lucky? But what if everything changes? What would happen then, if gravity got just a little stronger? What kind of trouble could that cause? If the rules of the universe changed, that would be unimaginable. In 1900, Max Planck was deeply troubled. He had been trying to understand, how does an object emit light when it goes from red hot to white hot? It's the same principle as other objects emitting light. He focused all his effort on the theory of light, towards James Clerk Maxwell's electromagnetic theory. In the end, it was the same as everyone else's. After all the struggle, he was desperate and failed. There was nothing he could do. He clenched his teeth, and threw the classic concept of heat energy aside. At the time, he still thought that the introduction of the concept of work was just a small mathematical trick. But who would have thought that Planck unknowingly invented quantum mechanics? Yes, Planck unknowingly invented quantum mechanics. Just this little trick. Quantization really works. Planck also, because of this, won the Nobel Prize in 1918. Just commend him for his profound insight. In his equation, there's a number crucial to his research. Now we call it the Planck constant, to commemorate its discoverer. This number plays a key role in quantum physics. It not only explains how hot objects emit light, atomic structure, matter, and the interaction of light, along with a bunch of strange quantum effects, are all explained by it. Planck's constant is one of the natural constants. These fundamental constants are crucial for studying hypothetical other universes. That's incredibly important. It's written in the language of mathematics. It is written in mathematical language. Through mathematical equations, we can predict the behavior of objects. For example, if we want to know how the moon moves, by combining Newton's laws of motion and the theory of gravity, we can calculate the moon's position tomorrow, next week, even 1,000 years from now. If you want to understand how electric current flows, use Maxwell's electromagnetic equations, plus the properties of electrons. The readings that amateurs are curious about, we can only estimate roughly, but physical equations are not pure mathematics. Relying only on mathematical calculations won't help you understand how things evolve. There's a key factor to consider as well. That's the value of natural constants. In Newton's law of gravitation, there is a gravitational constant. If you don't know its value, Newton's law of gravitation is just an empty framework. That gravity equation is just a hollow shell. The Einstein field equations are just empty words. Can't come to any conclusion. No matter what, I can't figure it out. In electromagnetism, there is magnetic permeability and dielectric constant. Maxwell's equations don't quite cut it for describing electromagnetic phenomena. To figure out the values of these constants, scientists have to learn from nature. We have to rely on measurements to obtain these values. In 1798, Henry Cavendish was again experimenting. He focused his eyes on the telescope. Guess what happened? This telescope isn't aimed at the sky, but through the bricks, looking out from a small hole in the garden shed wall. Why do it this way? To avoid interfering with this highly sensitive instrument, he hides it inside a wooden box in the shed, shielding it from wind and external environment. And the equipment itself, an extremely sensitive torsion balance was used, just to measure the gravitational force between lead spheres. Cavendish used this experiment to measure the density of the entire Earth. He even grandly called it weighing the world. This result directly advanced the calculation of the gravitational constant, and its precision went unmatched for the next 100 years. This pursuit of accuracy has continued to this day. Now, the gravitational constant g has been measured precisely to 6 decimal places. It's not just about gravity measurements. The speed of light is the ultimate constant in electromagnetism. Planck's constant. After decades of refinement, they are still related to the strength of the Higgs field, and the quark mixing angle. These deeper numerical values, together make up part of the natural constants. Aside from constants related to quarks, natural constants also include some values in the universe that cannot be derived purely from mathematics. They can only be determined through experiments. These values include the masses of fundamental particles, like the quarks and electrons that make up all matter. These values are too important. Physics textbooks usually list them in tables, so readers can easily look up physical equations in the book. Of course, check it out. Constants generally include units, and their units change from meters and kilograms to feet and pounds, and their units change from meters and kilograms to feet and pounds. As a result, the values of the constants change accordingly. So, scientists are more interested in the combinations of dimensionless constants. For example, mass, measured in kilograms, pounds, or grams. The proton's mass is 1,836 times that of the electron. But why is it 1,836? Why does this constant have to be exactly this value? What if this ratio were 18 or 18,000? What would the universe look like? And the topic circles back to the fine structure constant again. Why is its value 1/137? Theoretically speaking, we can try to answer these questions. We can consider different values of fundamental constants. In this case, solve the physical equations. In this way, we can figure it out. If the force of attraction is stronger than ours in the universe, strength 1,000 times, what would a hypothetical student love? For example, the Earth would be pulled closer by the Sun. We would orbit the Sun at a faster speed. But this isn't really what we want to explore. If we want to know what happens if the constants of nature were different, what will the universe become like? We have to consider the evolutionary history of the universe. Under different combinations of gravity, electromagnetic force, heavier electrons, or other varying physical conditions, we need to analyze from the very beginning state of the universe. We might initially think simply, believing this would change the complexity in the universe, and the possible timing of life's emergence. For example, increased gravity, and faster nuclear reactions, mean heavier elements could form earlier, and life might emerge sooner as well. But scientists have found, this idea is too one-sided. Astronomers, when explaining our universe, that was truly outstanding. They have always strictly followed scientific methods in their research. Scientific teams around the world are now using supercomputers to build their own synthetic universes. With these supercomputers, they can track the complex interactions of matter and radiation in the expanding universe. As computing power keeps soaring, the scale of the simulated universe is also getting larger, with velocity magnitudes, km/s, similar to well-known projects like TNJ and others. They have tracked billions of years. Within these simulated universes, a cubic region with a side length of 1 billion light-years, the process of cosmic evolution. During this process, cosmic expansion pulls matter outward in both directions. Gravity pulls them together again. Massive clumps gradually form into circular systems. At the same time, computers have to solve the equations of gas flows and turbulence in these synthetic universes. The equations governing gas flow and transverse formation. Stars in these synthetic universes, a spectacular explosion. Meanwhile, computer programs have been closely observing the formation and diffusion of elements, because generations of stars live and die here. Research on these synthetic universes has uncovered many rich structures, including synthetic galaxies and star clusters, as well as pure gas clouds left over from the Big Bang, and clouds polluted by heavy elements. These synthetic universes are quite similar to our real universe. This proves that the universe we see around us is determined by the fundamental physics of the cosmos. Our existence is the same way. The existence of complex molecules made of atoms is also a manifestation of this basic physics. It is also why stars can, at their core, the result of nuclear fusion. Of course, if we can generate a simulated universe on a computer, or even with pen and paper, then, in this hypothetical universe, it seems pretty simple to explore different physical phenomena. All we need to do is tweak the values of fundamental constants. Maybe if we analyze the computer code, we could see whether life's emergence was early or late, or even how it all ends for us. How many arms and legs can grow? Could it grow a few arms and 9 legs? But is it really that easy? We are, after all, over billions of years, in the universe's life, the product of a complex network of physical interactions. To truly answer the question of the universe's habitability, we need to understand how cutting off this interaction network, or opening new pathways, would affect the existence of the complexity required for life. Simple views may arise from simplified situations, But to truly capture the complexity of the universe, scientists have to rely on supercomputers, that immense computing power, to handle those tangled-up equations. They are still working hard, even now, trying to uncover the mysteries of habitability in other universes. It's worth exploring, the possibilities of multiverses that are countless, but the outlook is truly bleak. The calculations feel like peeling back a dark curtain, revealing a silent, dark ocean of death. Almost all other possible universes are barren wastelands with no life and ringing with poverty. In many of these universes, there are no structures at all, no galaxies, and no complexity. The periodic table of elements doesn't exist there. In these universes, which are almost dead, occasionally, a few scattered islands of complexity might appear. There might be life existing there. But such cases are extremely rare. Once in 100 billion years, let's take a few examples of what happens when natural constants are changed. In our universe, the relative masses of down quarks and up quarks basically determine that protons are lighter than neutrons. This causes neutrons to decay into protons. So, just after the Big Bang, the universe was full of protons. These protons are the core of every hydrogen atom, providing the universe with the means to form stars, and the potential to nurture heavier elements. Ultimately, they made it possible for our universe to create humans. If quarks were lighter than they are now, then this would change, and quark masses would become a big problem. In such a universe, neutron mass would actually be less than proton mass. After the Big Bang, the universe would turn into a sea of neutron-rich matter. Although it could form a neutron star, there will never be nuclear reactions in the universe again. No more blazing flames burning brightly. The periodic table of elements is a thing of the past. Matter isn't very complex either, let alone the birth of life. There's no way. Let's talk about electrons. It spins around the nucleus at lightning speed. The mass of the electron, it determines what the chemical world looks like, how matter combines into molecules and crystals. Nuclear forces are thousands of times stronger than the forces acting on electrons. But if the electron's mass were to increase, its high-speed orbit could make the nucleus shake and tremble violently. With just one tremor, the ability of atoms to bond is weakened. In the end, there might only be a single atom floating in the universe. All matter exists in gaseous form. Molecules, solids, all gone. The hope for life's emergence is completely shattered. A bleak darkness, a universe with different gravity, would be even more turbulent, perhaps even worse. In the early universe, gravity acted like a giant magnet, pulling matter together, hurrying the formation of the first stars and galaxies. If gravity were too weak, an expanding universe is like a thin, watery porridge, always maintaining a dilute hydrogen soup state. Stars can't form at all. If gravity is too strong, matter would be sucked into black holes as if losing its soul. All of it gets pulled into countless black holes, locking away the atoms essential for life. The very soil where life takes root would be gone. How does it give birth? Even if gravity is in the middle of these two extremes, it still plays a crucial role. The lifespan of a star is heavily related to gravity. Gravity pushes hard, squeezing the core of the star, squeezing it to the point where nuclear reactions can be triggered. But if not enough, a star becomes a huge ball of cooling gas, unable to produce the energy needed to sustain life. If the pressure is too great, the nuclear reactor runs wildly at super speed. Within a time much shorter than the sun's 10 billion-year lifespan, it burns all usable material completely. So, you see, long-lived and stable stars. Its gravitational strength is like walking a tightrope. It has to be perfectly controlled. In the end, even a tiny change to the values of those things we just learned would affect the universe's habitability today. That's a heavy blow. Dark energy is now the dominant force in cosmic expansion. In the early universe, matter was in control. The expansion of the universe gradually slowed down. About 5 billion years ago, dark energy began to dominate. The universe started to accelerate its expansion again. If there had been more dark energy in the universe, it would have taken control even earlier, perhaps in the universe, before the first stars had a chance to form, just pushing the universe to accelerate its expansion. In such a universe, a single hydrogen atom can only drift lonely in cold, empty space, all alone and isolated. The chances of life emerging are virtually zero. There's no hope at all. We can still think it over a bit. Other components of the universe, scalars like the speed of light and quantum mechanics, and the stability of dark matter, a part of the universe, the complexity and livability brought by the changes. But some others, even just a 1 or 2% change, can cause a tidal wave of upheaval, leading to earth-shaking changes. After considering all aspects of physics, many hypothetical universes capable of nurturing life have been ruled out. The universe we live in, that was a rare item. In the vast and endless sea of potential universes, actually, we're quite lonely. That being the case, first question, 8:13 How do we exist? So, I guess we have an answer. We are a nearly perfectly balanced system. Chlorine, over the long span of 13.8 billion years, the crystallization of interactions. But immediately after, a second question arises. What is all this really for? Natural constants, in the eyes of some physicists, always shrouded in a veil of mystery. They firmly believe there must be a reason for these specific constant values. Some people even fall into the trap of numerology. Shirley Eddington, an astronomer from Cambridge University, is one of them. He was also the first to experimentally verify Einstein's general theory of relativity. The result was the same as Feynman's. He also fell into the trap of the fine structure constant. Eddington was utterly fascinated by the crystal structure constant. Once believed he was exactly 1 in 137. He even came up with a wild conclusion, saying this value was related to the total number of protons in the observable universe. As the measurement accuracy of the fine structure constant improved, people discovered that it's not simply 1 divided by some integer. Eddington's idea was quietly set aside. However, the intrinsic connection between natural constants might be hinting at a deeper mystery. As scientific theories advance step by step, different parts slowly merge and unify. No, the fusion process is slow and unified. The number is also decreasing day by day. Before Maxwell, describing electrical and magnetic phenomena, requires 2 independent constants. Maxwell suddenly appeared. He unified the 2 into the natural constant of the speed of light. Is this the answer? What if physicists risk everything to create a theory of everything? Would all fundamental physics then be unified? By then, there will be no constants. Only pure mathematics remains. The concept of this ultimate theory is currently out of reach in the field of physics. Even if such a theory really exists, it seems it still can't untie the knots in our hearts, because we've only replaced one problem with another. Why do these mathematical expressions allow us to exist here? What he provides is nothing but another graveyard filled with silent, parallel universes. No explanation at all. The question remains unresolved. Why do the existing laws of physics just enough to bring us into existence? For some people, behind this fine-tuning of the universe's physical properties, there must be a fine-tuner, a divine being who created the universe for us. This aligns with many religious beliefs around the world. The fine-tuning argument is often seen as evidence that at least one God exists. But there's another perspective. Philosopher Nick Bostrom from Oxford University points out, now we all know that we can simulate various parts of the universe using computers. As future computers become more powerful, we'll be able to simulate even more complex aspects of the universe, perhaps even create conscious beings. As part of the simulation, these beings might be living leisurely in their own universe, completely unaware that the reality they are in is just a simulation. Maybe in the future, we won't just simulate one universe, but various kinds of universes. Each universe will have unique physical laws and properties. Of course, we wouldn't waste resources simulating boring and dull, lifeless universes. We focus only on interesting universes, like those where life arises. Bostrom further speculates. Could such simulations have happened long ago? Not in our universe. Our universe is just a simulation. Our laws of physics, it's just computer code running. So, if you find yourself in such a universe, we shouldn't be surprised, because it was that great dog programmer from the heavens who devised it. It's about investing resources in our safety, created this interesting simulation. This idea is deeply loved by philosophers. Scientists are not convinced. So what if we accept this concept? If what we do is just expressing computer code as physical laws, then we could test whether we're living in a simulation. Another question is, could the upper universe simulating our universe also be a simulation itself? Do we have to keep asking, with no end in sight? But there is another viewpoint based on a scientific hypothesis. What if all these possible universes are not just imaginary, but different universes within a real multiverse? At present, we don't have a mature, authoritative theory of the multiverse. It's more like a collection of various ideas. However, perhaps within the multiverse, there exists a process that generates a single universe. Each universe is born from its own unique physical laws. These laws are determined by random factors similar to metaphorical dice rolls. Even if we restart our universe, the physical laws at its birth could be completely different. Of course, under the multiverse framework, most individual universes are deathly silent and desolate. From this perspective, we are quite lucky to have the specific dice roll that allowed us to be born here. The concept of a multiverse has not gained widespread acceptance among cosmologists. They claim that in order for our universe to exist, creating so many dead, silent universes is truly a great waste. Someone also pointed out that the multiverse isn't even a true theory. It lacks mathematical support, and there are no testable predictions. After all, other universes are forever inaccessible to us. So, the issue remains clearly in front of us. Is it the whimsical ideas of the gods, or computer simulations, or perhaps the multiverse? Maybe one of these will ultimately give us the answer. Or maybe it's something even more bizarre. But before that, we must contemplate the way and reason for our existence. It can still reveal many mysteries about the universe, and the position we occupy within it. Everyone, that's all for today's episode. If you found it interesting, don't forget to like, leave a comment below if you have any thoughts. Finally, I wish you a good night's sleep. See you next time.